Good morning, and my name is Vinoy. I will speak to you today about bulk micromachining for the fabrication of microsystems. By bulk micromachining, bulk because you are basically etching into the bulk of the silicon wafer, we can form diaphragms or cavities as you see here, grooves or channels as you see here, or we could even form cantilever structures like this freestanding above a large cavity. We can also suitably modify the processes required and form tips, pyramidal geometries, conical geometries that could be used for applications such as in AFM tips. All these are possible by bulk micromachining. In this, unlike in surface micromachining where the microstructures formed are very thin, we can build much larger structures, cavities, so our channels by using bulk micromachining. Thin diaphragms are possible. We can even build, as I have seen, cantilevers by this approach. The silicon etching can be isotropic or anisotropic based on the type of reagents used. Isotropic, as the name indicates, would etch through all directions of silicon irrespective of its crystallinity. In anisotropic etching on the other hand, we can make use of the crystal nature of the silicon and the being rotationally asymmetric to build very interesting geometries. These are explained by the geometries here. What is formed by isotropic etching are usually irregular and depend on various process conditions. Whereas in anisotropic etching, we can choose the reagent so that it is anisotropic obviously and result in well defined side walls and to the cavities formed by etching. Depending on the silicon wafer crystallinity, the side wall could be different. We will see how and why about this a little later. One interesting thing to note at this stage is that the mask material used for defining the etch window is not photoresist, as you may have seen in other situations when thin films are etched. The etch process for thin films are fairly quick, and during the etching of the thin film, the photoresist that was covering it may not have gone completely. Whereas for etching silicon, more powerful etchants are required and usually for a longer time, and during that time the resist may not sustain, and hence mask layers are formed for creating etch windows. Silicon dioxide is a popular material for such mask windows. Silicon nitride is even better to function as mask window. What decides it is essentially the selectivity of the chemical that you would use for etching the silicon. So, in choosing the reagents for etching, we need to keep this aspect in mind. It should not, for example, etch the mask layer, or rather it should etch the mask layer far less than the volume, the bulk of the wafer silicon. Obviously, the steps involved are very similar to the overall process flow. The constituent steps include deposition, pattern transfer and etching. And in this case, various extended, lengthened etching steps are required to form the cavities on silicon. So, the emphasis here is on etching itself, but still all those unit processes are required for the successful completion of bulk micromachining. It obviously involves deposition of thin films, as you have seen, including silicon dioxide or silicon nitride. It would involve spin coating of resist or other materials. It may involve doping, as you will see later, to change the conductivity and the chemical activity of various layers. It would involve pattern transfer and etching. Etching could be done using wet chemicals or even be done in the dry phase. We will see many of these as we go by. Thin film deposition process would start from a source material from which the material is transported and condensed onto the substrate material. The quality of the film would depend on various parameters such as the substrate itself, the temperature at which it is kept, the gases that are flowing and the deposition, the rate at which the film is deposited. There are physical techniques for deposition in which we physically transfer the atoms of the material from the target, which is the source, to the substrate. We need to ensure favorable conditions for this transfer. There are chemical techniques of deposition in which we form the film material right on the substrate after a chemical reaction. So, the reagents are, as the name indicates, are in the gaseous form. You will see this in subsequent slides. In sputtering, as one of the physical methods is known as sputtering. In sputtering, we create a plasma with a neutral gas, and these ions that are formed will hit the cathode, and we keep the target at the cathode, so that the incident ions would displace atoms from the target, which is essentially the source material in this case, and the sputtered atoms from the target would be made to deposit or stick onto the wafer, which is kept at the anode. To ensure the reaction in this way, the transfer to happen in this way, we need to make sure that these are arranged properly within a vacuum chamber. The film grows on the substrate which is kept at the anode. In the chemical vapor deposition, on the other hand, the reactant gases are transported into this chamber, and we make sure the chemical reactions happen, and the film material is essentially coming out of the precursors that are there in the carrying gases, and the film, which is the product of the chemical reaction that is happening in the gaseous form, are absorbed onto the surface, and also we need to make sure that the other byproducts of the chemical reaction could be carried out in the gas flow. There are several variants of chemical vapor deposition based on the temperature or pressure at which these reactions are carried out. As I mentioned, we need to make sure the pressure, we can ensure the temperatures, and we can ensure the gas flow, so that proper deposition would happen at the wafer. It is possible to use the low pressure CVD techniques for depositing silicon dioxide from silane or from dichlorosilane or even from TOS. It is possible to deposit the silicon nitride by either LPCVD or PECVD techniques. One needs to ensure the process conditions, which are the temperatures and pressures, appropriately, so that the film growth could be controlled. As I mentioned, silicon dioxide and silicon nitride are useful as the masking material in bulk micromachining. Pattern transfer can be done using lithography or lift-off techniques. In lithography, we deposit the thin film first, and on top of that we put the resist by spin coating, which is soft baked and exposed to a UV beam, developed, and after one more baking stage, so that the resist would stick to the surface well, one can etch the thin film, after which, if required, the resist can be stripped off. Recall, this is once again, this is only for etching the thin film, this approach. To etch the silicon, we may want to keep the remaining thin film as the etch window. Etching of thin films silicon nitride can be done usually using phosphoric acid. Silicon dioxide can be done using the HF solutions. It may appear that the silicon nitride has lower or comparable etch rate as silicon dioxide, but it so happens that the nitride films are usually thinner and hence would work far better in the context of silicon etching. The etch characteristics are defined based on various parameters. Aspect ratio is the ratio of height to either of the lateral dimensions of the final microstructure. Etch selectivity is the ability of the process to choose between various material layers. In the example that you have seen in the beginning, it is essentially the selectivity between silicon and silicon dioxide. Unless there is a large selectivity, the etchant could attack the SiO2, and once that is gone, the structural definition itself will be lost, and hence a high selectivity is usually required. Etch rate is obviously the speed at which the desired material is removed by the etchant. Etch profile is the slope or the angle of the side walls after the structure or geometry is formed by etching. Wet etching involves transporting of the reagents and some kind of a chemical reaction and removal of the products of this chemical reaction. That is how we make the wet etching to happen. As I mentioned, one of the simplest things to imagine would be the isotropic etching. It is usually done by using acidic etchants and results in rounded patterns, as you could see from here. And these shapes are usually unpredictable and depends largely on the agitation and various other process parameters. It is also used, isotropic etching is also used when rounding of sharp edges are actually required. This is typically required to avoid stress concentrations. Isotropic etching can also be performed for removing surface roughness. It is useful when one would want to thin the substrate beforehand. It is useful even in patterning amorphous films or even polycrystalline silicon films. There are several instances in which isotropic etching is really required and useful. There are challenges in choosing the right etchants for various materials. The etch rates and most favorable solutions for etching of some of the materials used in micromachining are listed in this table. Anisotropic etching, on the other hand, make use of the crystalline nature of silicon in realizing well defined geometries. As you see from here, compared to the isotropic etching which results in rounded geometries and also what is known as undercut, which is essentially etching beneath the etch mask geometry. In anisotropic etching, if the geometries are decided well, we can ensure that there is minimal or no undercut and a continuous plane which would form the edge profile. Let us see how this is done in more detail. Depending on the width of the etch window and depending on the duration of the etch, we can have either a V shaped or a widened shaped cavities. Why is it so? It so happens if on a 100 wafer, if you align these rectangular or rectangular windows properly, the plane that is formed at an angle is 111 plane, and in atoms in 111 plane of silicon structure are strongly bonded to those underneath them, and hence are extremely difficult to be displaced by many reagents. We essentially exploit this feature to build such microstructures, cavities with regular well defined geometries. How does it form? Once this window is defined, as the chemical reaction begin, we get the top surface to be removed, but the last atom over here, which would eventually belong to this 111 plane, is very strongly bonded by atoms beneath it. So, it would be difficult to remove this atom here and on this side. So, hence what you would get would be an etched surface, but with the atom right beneath the etch window strongly bonded inward. And this process would continue, and the next 111 atom would be slightly displaced, and this atom also would be strongly bonded to the atoms beneath that. Hence, as the etching process continues, this plane gets defined and the etch floor would go down, but the side walls would not remain vertical or inward curved, rather it would remain as a continuation of the 111 plane starting from the etch window opening. This obviously is particular about 100 wafer. For a quick overview, we can look at how crystalline structures are defined. 100 surfaces are in which the wafer surface is aligned to any of the coordinate directions with respect to the lattice arrangement. In 110, the surface is diagonal with respect to two of the axes, whereas parallel with respect to one of the third. In 111, the surface of the crystal or the resulting plane is inclined with respect to all the three crystal directions. In the context of the silicon wafer, which is essentially a zinc blende structure consisting of two interpenetrating FCCs. If you recall, this is one unit cell of that with a dimension A, which is the single lattice constant. And if you look at the various crystal planes, in the 100 plane, within within a square of lattice constant A, we have all these 5 atoms, which are essentially the FCC atoms. In the case of 110 plane, which is shown here with this color, light green color, you have all these atoms marked with these lines lying on the surface, whereas all the other isolated atoms of the unit cell are off from the plane of this surface. Similarly, in a 111 plane, from the unit cell, these 6 atoms are on the surface. These 6 atoms are very strongly bonded to atoms close to them underneath within the unit cell. Hence, the structure of the silicon is not rotationally isotropic and the properties are different. And as you have seen here, in the once you hit this 111 plane, all the atoms are bonded very strongly to those below them and hence are difficult to be displaced. Hence, we get a smooth continuous plane if the etch window is aligned properly. So, unlike the rounded edge that is rounded profile that is formed in isotropic etching, in anisotropic etching, depending on the coverage area of the etch window, we can get a pyramidal shape or a truncated pyramidal shape in 110 wafers. Both these are for 100 wafers, I am sorry. Whereas, in a 110 wafer, it is possible to have a vertical side wall and these side walls are also at the 111 plane. So, all these will depend on the relative alignment of various directions, and hence we need to choose the window aligned with respect to the crystal orientation. For example, if the etch window is off from the crystal directions, as you see in the figure on the left, if there is a slight angle, what would happen is we will get a rectangular truncated pyramid in this case, but the base of it will not be aligned with respect to the etch window itself, rather it will be a superscribing rectangle from the etch window. And we can extend this and state that when the etch window is not rectangular, it would still be a truncated pyramid with rectangle base, not a circular base, even if the etch window is circular or elliptical. This is important to remember. The part of this could still remain, and we can extend what we said here to build freestanding structures like this. in silicon by micromachining. Obviously, what happens here can be explained in subsequent slides, how we can actually form such freestanding geometries. What happens while etching is that when we form this surface, let us say we use outside as the etch window film, we create this cavity, the hole here in the etch window, but as the etch progresses, what would happen is that a 111 plane would get formed here as well as here. It will get formed here, it may get formed here, here on this side as well as on the side below the protruding part. But yet the line here, the diagonal line here from this convex edge, the atoms on that side will not be as stable, because only if the plane is infinitely covered or entirely covered, the atoms are stable. In this corner, the atoms belonging to this plane or this plane are partially covered, and hence these corners will get attacked, and if you left it for long enough, there will be undercut, and this structure can remain freestanding at the end of the etch process. This is successfully utilized in realizing cantilever arrays of cantilever geometries in our labs. So, what is critical is that these edges are aligned with respect to the 110 directions on the surface of the silicon wafer. So, this gives you one significant reason in aligning the geometries with respect to the crystal orientation of the silicon wafer. Etchants used in anisotropic etching are usually alkaline aqueous solutions. KOH is by far the most popular material, and it has reasonable selectivity with SiO2. It is better with silicon nitride. The selectivity with silicon dioxide is of the order of 400 to 1. Another chemical which is used for etching silicon is known as EDP, ethylene diamine pyrocatechol, and which is a solution, aqueous solution of this. In this case, various materials could be used as the masking layer, and higher selectivity is possible for etching silicon. There are some basic issues in anisotropic etching, bulk micromachining of silicon. Because of these slanted side walls, larger real estate, larger area is required to form a cavity. This angle is predefined based on crystal directions, and as you may have noticed, is at an angle of 54.3 degrees with respect to the surface of the wafer, and hence for large area geometries, even larger area are wasted on the wafer, and this can potentially make the wafer fragile. What you see here is the etch selectivity with respect to various crystal directions of silicon when we use various reagents for the bulk etching. One needs to choose the right one so that a significant difference exists between the 111 direction and the other directions. There could be variations based on the composition of the chemical used, the temperature, and also the agitation. These variations are usually predictable as long as these parameters are kept within control, and hence the anisotropic etching is usually predictable for the overall geometries required. As we have seen, depending on whether 100 oriented wafer or 111 wafer is used, different types of sidewalls are possible. In 110 wafers, many of the sidewalls could be vertical. If you recall, it is not possible to form vertical sidewall, vertical directions from all the 4 sides of the cavity in a 110 wafer. You can only make 2 of the side walls vertical, and there will be some facets on the other side walls. Yet when you need a large vertical, a long vertical side wall channel, one can look at using the possibility of using 110 wafers for that purpose. As you may note, the sloping side walls can cause some inefficient utilization of the surface area. We can get nearly flat surface on the bottom floor after etching in 100. The multifaceted nature of the 2 opposite sides in 110 can cause floors which are not parallel to the top surface when etched using 110 wafers. Several interesting geometries, as you have seen, could be formed using 100 wafer. Can have diaphragms, we can have small cantilevers formed in 100 wafers. It is difficult to form such geometries with 110 oriented silicon. So, as I mentioned previously, based on the etch conditions, the etch speeds, and also the directionality, the suitable chemicals can be identified for building geometries. What you see here is a cavity formed below the diaphragm of a pressure sensor. In a pressure sensor, these diaphragms are stretched when pressure is applied. So, it has to be uniform and thin. So, we can do this by etching from the other side, and by having these regular side walls, which is a feature of anisotropic etching, we can have a predictable surface for the cavity. As you could see from here, the etched surface is inclined with respect to the silicon dioxide mask, which is largely unaffected in many practical situations. What you see here is one interesting geometry that could be formed by bulk etching. When we have these small windows and we start using isotropic etching, there will be undercuts, and as these undercuts, if the etch window dimensions are controlled properly, at the end of etch process, this is the outside that is remaining, and there is significant undercuts. If you remove this outside, we get nice conical geometries, and as I mentioned, these could be used for tips such as in atomic force microscopy. An important thing to note in the context of etching of silicon is about stopping of the etch process, especially in the context of the diaphragm that you have seen. We need to have a precise control where the etch process gets stopped. It is difficult to time the etch process so that you dig through this 500 micron of silicon if you are using a low diameter substrate wafer, and finish the process to leave a 5 or 10 micron thick diaphragm. Hence, alternate ways of stopping the etch process is required in these cases. One of the popular approach is based on doping the wafer appropriately. In doping, what we do is we introduce impurities and in a controlled fashion drive these in to the required depth, and hence there could be a significant variation in the etch rates based on the doping concentration. So, as you could see here, when there is 10 to the 20 per centimeter cube concentration, the etch rate drops to 0.015 micrometer per minute compared to 0.75 when the concentration is far less. So, the etch rate would be significantly lower when EDP or KOH or even sodium hydroxide is aqueous solutions of these are used for etching silicon. This feature can therefore be utilized for realizing a flat uniform thickness membrane for example for pressure sensor applications. As I mentioned, this would require doping. One of the approaches is based on what is known as diffusion. In diffusion, as in ion implantation, what is done is that we introduce N and P type materials onto the semiconductor. In diffusion, the wafer is placed in a high temperature furnace and a carrier gas is used, which is usually nitrogen, to transport the boron or phosphorus from the respective source material onto the surface of the wafer. After this is deposited onto the wafer, these are driven in by keeping it once again at a high temperature with a gas flow. So, we can dope the desired thickness of the semiconductor by suitably choosing the process conditions. We select the region where it is getting doped by using mask layers. Typically, silicon dioxide could be used for that purpose. For the successful realization of micromachining, often dry etching techniques are performed. Dry etching is similar in principle to the sputtering technique that you have seen in the context of deposition. In sputtering, if you recall, the ions from the plasma are made to hit the cathode where the target was kept. That causes the atoms to get displaced from the target. In the case of etching, what we do is instead of the target, we keep the wafer at the cathode. So, these incident ions would displace atoms from the surface of the wafer. It could be a physical phenomena if we are only looking at ion bombardment, but if reactive ions are used, obviously there could be selectivity and a chemical phenomena could be happening. So, there are several variants of dry etch possible and are utilized in micromachining of various microstructures. Compared to wet etching, this kind of dry etching is usually far more expensive. We need to carry out these reactions in a plasma reactor, which obviously at a low pressure, and hence all the additional equipment required for that purpose. We use corrosive acids and alkalis for wet etching, whereas we can live with oxygen, carbon tetrafluoride and other non-toxic gases for etching in the dry phase. It is easy to discharge the waste products in the case of dry etching and is easy to automate, and hence dry etching is usually preferred in the industry even though it is more expensive. Extended processes are required for high aspect ratio geometries. In wet etching, if you recall, when you start with 100 wafers, the aspect ratio is very limited and there is always wastage of wafer surface. Let us look at the various mechanisms that are possible in plasma etching. If you look at the simple physical removal, where only the ion bombardment could be used, there is chance that it is very poorly selective. And if you only look at the chemical reactions for the removal of material, it could happen that it is anisotropic. So, we need to have properly energized ions for good selectivity and anisotropy in realizing well structures with well defined profiles. Yet it may become a problem when you want to dig deep into the surface of into the bulk of the wafer. It often requires attaching inhibitors so that we can have a directionality in going deep into the wafer for deep structures with high aspect ratio. As I mentioned, in reactive ion etching, what we have is that we properly choose the ions in the plasma and make these to so that these react with only the desired material on the wafer. This can be used for patterning thin films and low aspect ratio geometries on silicon. Various materials could be patterned by suitably choosing the etch chemistry and the materials used or the gases used for within the chamber. For deep etching of silicon, for forming high aspect ratio geometries, processes known as deep reactive ion etching is required. In this case, what is done usually is that we remove material partially and then do a round of deposition scheme in which the side walls would get coated with something like a non-stick surface, so that a subsequent etching would, when the atoms get displaced, they do not go and stick to the side walls, rather they come out of the cavities. Hence, it is possible to realize high aspect ratio geometries using on silicon using deep reactive ion etching. Truly vertical side walls with very fine feature sizes are possible using this approach. As I mentioned, in this we can use various combinations of gases for etching various materials, yet we also use a step in which the side walls are coated with kind of non-stick polymeric surface. It may go away after some time. So, these removal and attachment processes are cycled so that high aspect ratio structures are possible. As in surface micromachined structures, bulk micromachined structures can also be integrated with electronics. These could be integrated on chip or even at the packaged level as multi-chip modules. But in bulk micromachining, you can only have cavities as deep as the wafer thickness. When we want to really thicker geometries, we want to look at possibilities of bonding multiple wafers and processing them further. On the other hand, when thin microstructures are required, we look for surface micromachining. In this example, cantilever structures are formed and where polysilicon is used as a structural material and silicon dioxide can be used as the sacrificial material. Compared to surface micromachining, bulk micromachining allows removal of significant amount of materials and hence larger structures are possible. In both surface and bulk micromachining, dry and wet etching are utilized effectively. The dimensions of structures formed by surface micromachining can be several orders of magnitude smaller than in bulk material and can have very large lateral dimensions and very thin vertical dimensions. As you could see from here, in surface micromachining you are essentially adding a small component to the surface of the silicon wafer, whereas we dig into the wafer itself in the case of bulk micromachining. Various components have been demonstrated using both these techniques and have become the mainstay in building microsystems. So, both surface and bulk micromachining techniques are important. Thank you very much.